All right, this is section 1.8, continuity. So first thing, once again, let's get rid of this. This is not your homework. It will, of course, be WebAssign. So we'll put that in there. Okay, so we're just going to basically identify continuous and discontinuous functions, and we're going to talk about the definitions and how all this works. Continuity, for the most part, if you're thinking about a graph, should be actually something most of us can kind of figure out. If something is continuous, it means it doesn't stop, it doesn't break, it doesn't have any kind of issues where you've got some kind of a like I said, like a break or a hole or something like that in the graph. It's continuously, or that's kind of a bad way to start because you can't really use the definition in the word, but it just doesn't stop. Okay, it never has any kind of a break in it. And again, I think most of you can probably picture that in your head. But what is the actual definition of continuity at a specific point? So we can kind of picture what a graph that is continuous looks like in our head, but what would it be actually to define something being continuous at a specific point? Well, if a function f is continuous at c, and c is just the x value that we're talking about, three things have to be met. There are three conditions. The first condition is that f of c, or the y value when you plug that x value in, is defined. Okay, you actually have to have a y value there. If there's no y value there, it doesn't make sense. It would not be continuous because it wouldn't even exist. The second condition is that the limit as x approaches c of f of x exists. So we basically have to have a point, f of c, and the limit as x approaches c has to exist. And in order for something to be continuous, those two things have to be the same. So 1 and 2 have to equal each other. So the limit as x approaches c of f of x equals f of c. Okay, and that is how you define something to be continuous at a point. It must meet those three conditions. In other words, a function f is continuous at a number c if the limit equals the function's value at that particular place. All right, so normally I would have you probably do this in class, but since this is going through our lesson, we're going to draw a function where the first condition is true, but the second one is not, to show you how sometimes these things may not actually work. So let's draw one. Here's an xy axis. Let's draw something where the first condition is met, so f of c is defined, but the second one is not, so the limit doesn't exist. Well, okay, so let's put c on here somewhere. We'll call that c. Now, f of c has to exist, so that means there has to be a value there. So let's go ahead and put a point there. Well, here's an easy one. If I go that way, so far f of c exists. We don't want the limit to exist, though, so let's do this. Let's go ahead and put something down here like this. Now you can clearly see that the limit here would not exist because the limit is going to be two different values as you approach from the left and the right. So the first condition is met because f of c is defined. The second condition is not met. The limit doesn't exist. All right, so now let's take a look at the second one here. It wants us to do where the second condition is true, but the first one is not. So this time the limit has to exist, but the function does not exist. Okay, again, let's put a c on here somewhere. Call that one c. So the limit has to exist, but the function does not exist. Well, that's pretty easy. You just put a hole wherever that is. So we could do any kind of a thing that we wanted to graphically. Any kind of a thing that comes there, and then we'll put a hole there, and then it continues to do this. So the limit is going to exist. The limit is going to be there because both of the sides of C, the left and the right side of C, are going to approach the same y value, but there's actually no value there at all. So second condition is true, first one is not. And then the last one wants us to do one where both of the first and second conditions are true, but the third one is not. So let's go back. So we need there to be an actual defined value of C at C. We need the limit to exist, but those two things can't equal each other. Well, we can actually kind of take a very similar approach to the one that we just did. I'm going to try and sketch something close to that if I can. Doesn't have to be exact, but so the limit here exists. I want the function to exist. Well, let's do this. Now I've got a value at C, but the limit's value, the limit and the function's value are not the same. So there are three examples of where you can have some of these conditions true, but not all three of them are true. In order for something to be continuous, all three have to be true. So there's three examples of where that doesn't happen. All right, so let's talk about discontinuity. Okay, and as you would assume, discontinuity means not continuous. So here we're going to get into a lot of math speak. I will, again, try and break this down as much as I can for you guys. So hopefully it makes sense, because there's going to be a lot of terminology which you're probably not used to seeing just yet, but we'll get there. So consider an open interval I that contains a real number C. If a function f is defined on I, except possibly at C, and f is not continuous at C, then f is said to have a discontinuity at C. And there are two types of discontinuities. Okay, I seriously doubt all that made sense the first time through. So let's go back and kind of think about this. First of all, talking about an open interval. That means the endpoints are not included. And it would be illustrated with some kind of parentheses like that. And it would go from like A to B or something like that, or 2 to 7 or whatever. But the endpoints would not be included on an open interval. And they're calling the open interval I. Within that open interval, you're going to have a real number C. So C, again, is just some x value in between A and B, or in between your endpoints. If a function f is defined on I, so it is defined there except for possibly at that C value. So maybe it's not defined there. And f is not continuous at C, so it fails the previous three, or at least one of the previous three parts of the definition of continuity, then f is said to have a discontinuity at C. So if it fails one of those three things, it's going to be discontinuous at C. Hopefully that makes sense. And again, there's really there's really three types. Two of them fit kind of in the same category. So we're going to add like a 3 down here. But the last two are really kind of the same category. So the first kind is what's called a removable discontinuity. Removable. Okay, and a removable discontinuity typically is a hole in the graph. And the reason it's called removable is because we can actually manipulate the function or redefine the function so that we can get rid of the removable discontinuity. And the second two are what are called a jump discontinuity. Oops, learn how to spell. Discontinuity. And then the other one is an infinite discontinuity. Infinite discontinuity. All right, and an infinite discontinuity is going to be your vertical asymptote. Both of these two are what are called non-removable. Non-removable. And they are non-removable because there is no way to redefine them in a way that you can actually make them continuous. So again, kind of like what I said before in number 1, a discontinuity at C is called removable if f can be made continuous by appropriately defining or redefining f of C. And we will show an example of that. First of all, Let's look at these functions and just determine, first of all, whether they're continuous or discontinuous. And if they are discontinuous, then let's try and figure out what type of discontinuity we have there. So the first one, f of x equals 1 over x squared plus 1. Remember, for something to be discontinuous, the easiest thing to look at when you've got a fraction is, does something make the denominator 0? Well, can I plug anything in for x to make that denominator 0? And the answer to that is no. X squared plus 1 cannot ever be 0, at least not in the real numbers. We're not dealing with imaginary. So in this case, the answer to that is no, which means this is continuous, which is nice. There is nothing else to answer there. It's just continuous. Again, x squared plus 1, the smallest value it can possibly be is 1. You're good. It's never going to be 0. The one on the upper right, x squared minus 1 in the denominator, well, that can be made 0. As a matter of fact, there's two values that can make that 0, and that's plus and minus 1. So it's discontinuous at x equals plus or minus 1. And because neither plus or minus 1 makes the numerator also 0, it's not a whole, which means this has to be an infinite discontinuity. Infinite discontinuity, which means it is not removable or non-removable. All right, let's look at the one on the bottom left. It's a piecewise function, f of x equals x as long as x is less than 1, f of x equals x squared as long as x is greater than 1. So if we were to kind of sketch what that is, because a lot of times piecewise it's easier to tell. As long as f of x is less than 1, that means it's y equals x. So it's going to look like this up until it hits 1, and it's not going to be included, so you get a hole there. And then f of x equals x squared as long as x is greater than 1, which is your parabola. So starting at 1, it's going to start to do this. So what you should be able to see here is pretty clearly that you have a limit. The limit is going to approach the same y value as x approaches 1, but there's no value there at x equals 1. And I know that because there's no equal to symbol underneath of either one of those pieces. So this one is also discontinuous. Discontinuous. And this one right here is actually removable because it's a whole. And how is that removable, you might ask? Well, we're not actually going to do it here, but let's say I redefined f of x and added a part in there that said x is going to equal f of x equals 1 when x equals 1, that would fill that hole in, and then it would become continuous. Okay, so you could technically redefine that in order to make it continuous. You can't just arbitrarily redefine a function, but that's why it's called removable, because if you could redefine it, that's what you would do. And then the last one is f of x equals tangent of pi x over 2. So in order to know this one, you kind of just really need to know what the graph of tangent looks like. And our graph of tangent looks something like this. And that goes on infinitely forever in the left and right direction because, if you remember, tangent has vertical asymptotes. And then it keeps on going to the right and to the left of those vertical asymptotes, and there's really an infinite number of vertical asymptotes. So that really ought to tell you right away, because there's vertical asymptotes, it's discontinuous. So this one is going to be discontinuous. And these are infinite discontinuities, and they are non-removable. All right, again, hopefully that makes sense. Oh, by the way, and these were at pi halves and negative pi halves, just to remind you that's where the discontinuities were. All right, let's move along. We have these things which are one-sided limits, which we have talked about. One-sided limits and continuity on a closed interval. So now we're talking about things where the endpoints are included. And remember, a closed interval is going to look something like this. It's going to have closed off brackets, and the endpoints will be included. So like A and B or something like that. One-sided limits are useful in taking limits of functions involving radicals. For example, if n is an even integer, then you're going to be taking the limit of the nth root or an even root of x. And we know that those have domain restrictions on them. So the limit as x approaches c from the positive side of that is going to go to 0 in this case. So let's go ahead and take a look at what that means. So the limit as x approaches 1 from the positive side of the square root of x minus 1. Well, if you think about the graph, it's a square root function which has been shifted 1 unit to the right. So it's going to start here. Whoops, did not mean to erase. It's going to start here, and then it's going to look like the square root function, something like that. Well, so think about this. The limit as x approaches 1 from the right. As I approach the value of 1 from the right side, the y value is clearly approaching 0. But the question is, what's the limit of the same function as x approaches 1 from the left? It's kind of a trick question because of the fact that there is nothing to the left of 1. The function ends at 1. So because of that, this does not exist. Okay, there is no function to the left of 1, so you cannot approach 1 from the left of 1. There's just no way to do it. So that's why a one-sided limit is important for continuity, because this thing is continuous at x equals 1. Because it's continuous from the right, it can't be continuous from the left just because of the fact that there is no function to the left. Again, hopefully that makes sense. All right. Now let's think about these greatest integer functions. So the greatest integer is that one where you're looking at the values, whatever the integer is, it's the next integer less than the one that we give you. So if I want to take the limit of the greatest integer of x as x approaches 7 from the right side, so we're talking about values like 7.1, 7.03, 7.01, 7.000001, values that are getting closer and closer to 7 from the right side. Well, all of those numbers are a little bit bigger than 7, so all of those go to 7 because it's the next lowest number. So all those things are going to approach 7. Now the trick is, think about this one. Now it's as we approach the limit as x approaches 7 from the left-hand side of 7 now. Now you're actually talking about the values which are coming from the part where it's actually on the line of 6. And again, let's just kind of sketch this real quick. And I'm not going to do every single number, but we'll call this like 7, and we'll call this 6. So from 7, it looks like this. And from 6, it looks something like that. And we'll say that that's 6 and that's 7. That is definitely not drawn to scale, but you get the idea. So as you approach 7 from the right, oops, you're coming from this side. And then as you approach 7 from the left, you're coming from this side. So as we approach 7 from the left, you're going to have values which approach 6. As you approach 7 from the right, the values approach 7. So what then would be the limit as x approaches 7? Well, those two things are different from either side, so this does not exist due to differing behavior. And it's quite clear to see that this is not a continuous function, and it's not going to be continuous at any one of those integers because of that. Now, is it continuous in between all the integers? Yes. You can see how each one of those things is a solid straight line in between both of the integers. All right, let's talk about continuity on an open interval. So continuity on an open interval, again, remember open interval means not including the endpoints. So the function is going to be continuous on an open interval if it is continuous at each number in the interval. So it's got to be continuous at everything in between a and b. A function that is continuous on the entire real number line, which is from negative infinity to infinity, is called everywhere continuous. I think I keep misspelling this. I'm leaving out the extra O. There we go. It's called everywhere continuous. Why it's not called continuous everywhere, I don't know. You can say it that way. It doesn't make any difference. If f is continuous, really going to get a lot of practice trying to spell continuous here. This one up here is not right. U-O-U-S. There we go. If f is continuous on one side of an endpoint of the interval, we understand continuous at that endpoint to mean continuous, really should know how to spell this word from now on, from the right, or continuous from the left. That again, it's only if it's continuous from one side, but not necessarily the other. Let's take a look at what that means. Something like this up here. This thing would be continuous as x approaches 7 from the right side only, because this direction is what makes it continuous. As you approach 7 from the left side, this is not continuous because it's an open circle. The closed circle means that it is continuous from the right. Hopefully that makes sense. Must be approaching a closed circle to have it be continuous from the right or from the left. If it approaches an open circle, not continuous there. All right, and we're going to do the top of this next page here, the definition of continuity on a closed interval, and then we'll come back and actually finish this off in a second video. All right, so the definition now of continuity on a closed interval. Remember, that includes the endpoints. So a function is function f is continuous on the closed interval from a to b if it is continuous on the open interval, so everything in between a and b, and this is the important part, the limit as x approaches c, I'm sorry, a, we're using a now instead of c. Oh, a is the left endpoint, from the right side. Now think about that. The limit as x approaches a from the right side. It's a closed interval from a to b. So whatever your function looks like from a to b, say that's a, we'll say this is b out here. There's no way to approach this from anywhere except for the right side of a. Can't approach it from the left side of a. So it has to be the limit as x approaches a from the right of f of x. Well, that has to equal f of a. And that comes straight from your definition of continuity, that the limit has to equal the function's value. Same exact idea going the other direction. The limit as x approaches b, and the only way you could approach b is from the left of f of x, has to equal f of b. The limit must equal the function at that point. So it's got to be continuous at every interior point, and then it has to be continuous at the end points, but that to show that, you have to take the limit as you approach it from the specific direction that you can approach that endpoint, has to equal the function's value there. All right, that's good enough for this video. We'll come back with a second video and finish it off.